So thank you very much for having us here. At first, I would like to wish, on behalf of all of us, happy birthday to Ruth. It's her birthday today. Okay, so yeah, I'm CTO of Mellanox. We are an Israeli company that started in '99. Now we are a public company for quite some time. I realized that it is a really hard time after lunch, so I will try to make my talk as simple as possible. I thought about bringing up a lot of code examples and formulas, but at some point decided to drop it off. So for those of you who want to sleep well, you can read this. And now I will move to the some stuff that I wanted to talk about. So now we live in the wave of data, and the amount of data that's being generated by various sensors exceed by far what has been stored and developed before that. In less than a week of Facebook generates more data than it is today in the Library of US Congress. And one flight of Boeing generates even more data than that. So this tremendous amount of data makes the data to be a resource, as oil or nafta or gas used to be a resource in the previous century. Today, data is a resource. And this resource can be put to use for both security and governments, but also for people. The example of data usage for government is that, in the Boston bombing a few years ago, the way these guys were found is that NSA pulled out of the cell phones of the people, that were around, all the photos or media that was there, processed this data on their computers and identified the guys that planted the bomb. Another example of using the data for more civil purposes is Waze. In 2007, Nokia bought Navatech for $8 billion just to get the access to 5 million traffic sensors that Navatech owned in Europe. In the same year, Waze started in Israel, and they got 50 million sensors for free. So, and now everybody, at least in Israel, everybody uses Waze, and we can't get around there. So the data is the resource. It is like raw resource. And the way to make this resource to use, similar to big power plants, there's the big data processing plants that are getting this data and transforming it to information that becomes available to everyone, that information that becomes available even before we ask for it. I was biking today, and all of a sudden I figured out that Google figured out that I was biking and telling me that I need to bike a little bit more, a little bit less. So the data processing plants, similar to power plants, are huge infrastructure built by companies like Google, eBay, Baidu, and others. And the way they, in a sense, they're taking this data and using a lot of compute elements on one side and storage elements and providing this information to the application that we access the data through. And the way to make all this stuff works, all this stuff put together, is the network. Is the smart network that everybody is building using various technologies. A lot of them are using our technologies. And making this data available to everyone, everywhere, at any time. This is the example of health and traffic engineering and security and all the things about the Internet of Things. Is basically taking the data that every one of us generate and make it available as information to everyone else. The huge style of data made a transformation of the way these data centers are built and data is processed. All the data center architecture and data center, the way data center is thought of is actually changing as we speak. And the reason it's changing is because in the traditional data center, what used to be is that every consumer or every customer of the data center has its own data and its own application, usually running on the client machine, and therefore the data traffic was vertical. So from the data stored and some computed on the data center all the way to the client, and there was relatively little what's called east-west traffic. So the compute element, the elements of the data center didn't communicate too much with each other. Today, there's much more communication within the data center than outside. The vast majority of communication and data processing is done between the various elements within the data center, and therefore east-west traffic becomes much more prevalent than south-north. So this drives the rethinking of the data center, and this is the building block, the compute node. This is the building block of the computer. What you see here is the CPU, the central processor unit, that's the way it's called, is in the middle. It is optimized to access local storage, local memory, I/O, but the data is a sort of afterthought. The data is the way to the traditional computer accesses the data is that it has to be local, it should be in the memory, and all the optimizations are done in the local data processing. So the Web 2 and the cloud data centers are actually built around the data. There is a data flow, there is a data which needs to be available everywhere. CPU becomes, from central processor unit, it becomes computational peripheral, and the data is in the center, the storage in the center, and the way the data is steered and the way its data becomes available to various applications that are running on different elements on the data center. This is the key to the success of the data center. And one of the important things is that there should be segregation between where data resides versus where it's being processed. If in the traditional data center, data is processed on the local node, on the local computer, here we need to be able to segregate the data residence and the data processing part. So there are some technologies that are built around it. And when we optimize the data center, the single server or single compute block is not a unit of optimization anymore. We optimize on the data center per se, or little rack. Rack is the little data center that is instantiated. And so there's several elements out of it. One is the ability to segregate the data and the processing, which means that every compute element needs to be able to access the data on any other compute node without disturbing that node or that element that it accesses the data through. So this is what's called RDMA, remote direct memory access. Any application, any machine on the data center should be able to access the memory on any other machine without disturbing the application running there. The other part is how do you partition different logical elements, which is a processor, memory, and the network. And last but not least is actually how do you move the stuff at the speed that's required. Today, when we talk about accessing the memory on the remote, it needs to be the bandwidth and the characteristics of the access should be significantly higher, faster, and significantly higher performing than traditional network. So the way to do it is the silicon photonics. There is optics technologies that is being now much more and more adopted in the data center to run at networks at high speed. So another thing is that how we actually process how actually the data access is being processed. One is what's called CPUnload. It means that CPU is involved in every data processing, be it local request or remote request. And as a result, for the high-speed networks, the amount of processing power that you need to invest to process such data is fairly significant, and it goes on the expense of compute power that you could have be using to run the application. And therefore, it's very significant CPU consumptions as well as very low, much lower performance. RDMA, this technology to be able to access the remote memory transparently to the target node, this is what comes to solve this issue. Another part is different partitioning between the compute and network elements. One of the things is we call it multi-host technology, which enables to aggregate multiple compute nodes on a single adapter for the network access. And the key here is that the two pictures on the right and the left are completely equivalent from the software perspective. Each one of the compute elements on the right-hand side sees its own virtual adapter instead of inside the adapter on the left-hand side. The way to utilize it is that you actually have multi-socket machines, and the reason they build multi-socket machines is not always because you need high core count SMP processing, but it is just for the economics of how you build the server. So using the multi-host technology, you can have each own CPU or its own socket access to the network on its own. And this enables you to, first of all, much more efficient access to the network. It's now symmetrical. And also, you can use much lower cost processors than multi-socket processor for the four-way architecture. And this is actually what is built by Facebook. The Facebook introduced this OCP, Open Compute Platform, in March this year. And there is an available reference design that uses our adapter and up to 4 cores, up to 4 compute elements that are aggregated together. And this little box actually represents 4 compute servers connected to the network on 100 gigabit per second. So we have introduced 100 gigabit per second technology. Today it's available for sale in the store near you. Adapter, switches, and the cables. And what Andy Grove said about 30 years ago, we need to eat your own dog food. So we are building these cloud platforms, and we use it in our data centers and also make it available to our customers to run their applications and to try out their technologies. So that's about it. Thank you very much.